in the next few lectures what I would be doing is discussing how to go about doing energy band calculations. So, first of all, to obtain energy bands of a crystal, we have to solve the crystal Hamiltonian. Okay, the crystal Hamiltonian is given by H crystal is equal to minus h cross squared by 2m del squared plus V of r, and V of r has the periodicity of the lattice, which means V of r plus Rn is equal to V of r. So, this also means that the Hamiltonian has the periodicity of the lattice, that is H crystal R plus Rn is equal to H crystal R. Of course, we have Rn is equal to N1A plus N2B plus N3C. N1, N2 are integers, N1, N2, N3 are integers, and A, B, C are primitive lattice translation vectors. A, B, C are primitive lattice vectors. Well, we also said that given this, we have the Bloch's theorem. All this is actually recapping. Psi k r plus Rn is equal to e to the power I k dot Rn psi k of r. I can write it as psi k of r is equal to e to the power I k dot r u k of r, and u k of r, as we have already seen, should have the periodicity of the lattice. I also said that we have the reciprocal. If I look at plane waves of this type, that is e to the power I km dot r, km are reciprocal lattice vectors. Then what we have is e to the power I km dot r plus Rn is equal to e to the power I km dot Rn e to the I km dot r, and we said that km dot Rn is equal to 2 pi times integer, and we also said that earlier that km is given by M1A plus M2B plus M3C, and with A, B, C given by 2 pi B cross C by A dot B cross C and cyclic. So, with this, what we know is that e to the I km dot r are basis states which satisfy the Bloch's theorem, Bloch's condition, theorem, whatever you want to call, is actually a boundary condition. And what we know from this is the following, that is, this is one type of basis that we can have. Another kind of basis that we can construct which satisfy the block condition are tight binding functions. These we encountered when we were discussing pictorial representation of energy bands, tight binding functions. So, these functions can just simply be written as phi n of r is equal to sigma over Rn e to the power I k dot Rn times Un r minus Rn. So, like we had already said that before, Rn runs over is over all lattice points, and Un r minus Rn is the atomic or molecular orbital at the lattice point Rn. Now, we can see very simply how this satisfies the block condition. So, we take this phi n k, because there is also a label k associated with that. Phi n, because it is the orbital is of the n type, n can be 1s, 2s, 2p, etc. So, n can be 1s, 2s, 2p, or sigma 1s, sigma star 1s, etc., etc., etc. We will worry about it as we go along. Okay. Now, to show that phi n k r satisfies Bloch's theorem, all we need to show is the following: phi n k r plus r m is equal to sigma over r n e to the power I k dot r n u n r minus r n plus r m. So, one can actually write it in this following fashion, that is, I can write it as sigma over r n e to the I k dot r n u n r minus of r n minus r m. I can write this as sigma over r n e to the I k dot r n minus r m into e to the I k dot r m u n r minus of r n minus r m. Now, you see the following, that is, r n minus r m is also a lattice translation vector. Say r k, and summation r n can be replaced by r k as it is a dummy index. When we say it is a dummy index, that means that whether since you are summing over it, it does not matter what you call. Okay. For example, sigma over I xi is equal to sigma over j, xj and so forth. So, they are all one and the same. So, because of that I can write down phi nk r plus rm as equal to e to the ik dot rm sigma over rk e to the power I k dot rk un r minus rk, and this is equal to what we have here is this is nothing but u phi n of r so we have this is equal to e to the ik dot rm phi n k of r. So, you see that you can also construct block functions using tight binding molecular orbital atomic functions, just as you also had block functions which are just plane waves. These are the two extreme limits of the kind of basis that you can think of. Well, now let us come to what are the things that need to be known if you have to actually solve for the energy bands. So, we have the following unknowns in the Hamiltonian. Or V of r, the crystal potential. Depending upon the kind of approximations you do for V of r, you can have different kinds of methods, and we also have bases. So, we can have different kinds of bases. Plane waves, tight binding functions, etc., etc. I will come to other kinds of bases a little later. Now, having said that, so we need to construct the Hamiltonian for every value of k. So, if you look at the Hamiltonian, it has got the periodicity of the lattice. So, which means that you have psi k h psi k prime, where h is the crystal potential, crystal Hamiltonian is actually can be simplified, because you can know you put a condition on k and k prime, because the potential is periodic. So, the Hamiltonian is also periodic. So, once the Hamiltonian is also periodic, then if I am looking at psi k h crystal psi k prime, then I can actually write it as psi k sigma over m h k m e to the I k m dot r times psi k prime, and this turns out to be just nothing but, we did this earlier in the nearly free electron model, and so this turns out to be just h k k prime delta k minus k prime comma k m. So, what it means is that unless the wave vectors k and k prime are connected by a reciprocal lattice vector, the Hamiltonian matrix element is 0. So, this has many advantages. What it means is that this implies the above condition implies we need to solve the eigenstates for a given k every time. that is each time. So, you do not have to mix up different k vectors which are not related by the reciprocal lattice translation vector. So, what happens is that you have this. So, you have eigenvalues are all going to be eigenvalue of k epsilon k plus k1 epsilon k plus k2 etc. is what you will get as the eigenvalues. So, if you use like n this thing reciprocal lattice vectors in the basis, then you will have all the way to e to the power k plus kn. So, that means you will have like n plus 1 solutions, and these correspond to, this will be the first band, this will be the second band, and so on and so forth. This will be the third band, etc., etc. So, basically you see a crystal, if you are looking at a crystal, it has infinite number of lattice points. So, if it has infinite number of lattice points, then it means that if you do not use any symmetry whatsoever, then you will have infinite basis, corresponding to all possible values of k and corresponding to all functions at every lattice site. So, even if you truncate it, you just have to like Hamiltonian matrix will be of the order of n, that is it will be a n by n matrix where n is the number of lattice points. Even if you consider just one plane wave per site, okay. But if you have, that is if you just use one particular function, okay, like say for example the this thing 1s function in the tight binding, even then if you do not use any of the symmetries, then what happens is you have got n 1s orbitals, and the Hamiltonian matrix has to be represented as an n by n matrix where n is the number of lattice points which is of the order of Avogadro number of the order of 10 to the power 23, and you will have to solve it. So, this is a very very difficult thing to do. So, what one does is if you use translational symmetry, we solve a smaller problem size of the Hamiltonian matrix size of H matrix is the size of number of orbitals, size of the number of orbitals per site, but you have to solve this at every k point. But this smaller problem needs to be solved for every value of k in the Brillouin zone. Of course, if you are speaking theoretically, then the number of k points in the Brillouin zone is also infinite. But what we usually do is the following, that is we solve for eigenvalues at grid points in the Brillouin zone. So, for example, if the Brillouin zone is a square Brillouin zone, let us say, So, in this what you can do is you can put this grid, which is actually say a 5 by 5 grid you can put, and you can solve at central at the middle points of the grid. Interpolate the results so that you would get the energy levels for desired k points. So, you can always interpolate between grid points. So, this is a great advantage if you use the translational symmetry, and that is why you use the Bloch's theorem, the translational symmetry whenever you are doing energy band calculation. Now, you see what another thing that one should realize is that the Brillouin zone has lot of symmetry. So, the question that we ask is it necessary to do the calculations at all points in the Brillouin zone? To answer this question, what we have to do is we have to go back to the symmetry operations of the direct lattice. Okay. So, let us look at this a little more carefully. So, what we have is you look at the symmetry operators in the direct lattice. The symmetry operator in the direct lattice is given by from the space group operators are given by R is the operation, which is a point group operation, times some translation which I will say is A. The translation need not be corresponding to a lattice vector, but if I am looking at symmorphic space groups, then A corresponds to a lattice vector. So, that R itself is a subgroup of the space group. Well, given this, let us see what this does on a vector. So, if I take the operator R of A and operate on a vector x, then what it is going to give me is R times x plus A. So, it basically first does a rotation or reflection, whichever is operation that you are performing, which is given by R, and then making a translation. The translation can be A is equal to R, A is a direct lattice translation vector for symmorphic groups. For symmorphic space groups, it is a direct lattice translation vectors. For non-symmorphic, it need not be a direct lattice translation vector. Now, there is what is called a Wigner notation. In the Wigner notation, see here we are acting by this operator R of A on a vector, but how does R of A operate on a function? This specifies how R A operates on a function. So, the way it operates is the following, that is, if I take f of x and operate this by say the operator which operates on functions which could be different from R of A, but represented as P times R A. So, this is just to show that P is the symbol that is just used to show that it is actually operating upon the functions and it is not operating upon the vectors, and the operations P R comma A are homomorphous with respect to the operations R A. So, they have all the elements that you have in R of A. So, they are both P R A and R A actually form homomorphic groups, and so this is given by f of R inverse x minus R inverse A. So, this is something that the function variable is rotated opposite the way the coordinate system is rotated. The coordinate system is rotated by RA, but the variable is rotated in the reverse way so as to compensate for that, but this is usually the convention. Now, let us see what else we can do. So, we can think of operating by RA on a plane wave e to the power ik dot r, or in our case, yeah, we will take it as e to the power ik dot r. So, if I take this, then this is going to give me e to the power ik dot r inverse times r minus r inverse times A, exactly the way I have written above. So, this is actually what I can also write it as PRA is equal to f of R A inverse operating upon x. Okay. So, this is what this quantity stands for. So, this I can write it as e to the power I k dot r inverse r into e to the minus I r inverse A. Now, let me look at k dot r inverse A, r inverse r. Look at k dot r inverse r. Okay. So, see, r is a unitary operator. When we say r is a unitary operator, it is actually norm preserving operator or the inner product preserving operator. So, which means that r any vector A dot r any vector B is equal to A dot B. So, if I did that here, what I will have is R k dot r inverse r is equal to k dot r inverse r. So, this will be r inverse is actually the identity. So, this will be just r k dot r is equal to k dot r inverse r. If A is a lattice translation vector, then R inverse A is also a lattice translation. Following psi k of r, which is a block state, and I operate on this by P R A is a lattice translation vector, then this is going to give me psi r k times r. Okay. And if this is true, if the energy of the state psi k of r is non-degenerate. If it is degenerate, it means that energy n comma k is equal to energy 1 comma let me put it this way, sorry, energy 1 comma k, energy 2 comma k, etc. up to energy E n comma k, and my operator P of R A on such a state psi of k of r would give me sigma over I equal to 1 to n, say let us say 1 comma k. So, C 1 comma I psi of r k comma I. Let me, the indices are interchanged, psi of I comma r k. Okay, so that is in that particular case. So, but nonetheless what it means is the following. That means that the energy of the states at k and r k are the same. So, we need not calculate eigenvalues for all k points in the Brillouin zone, but it is enough to calculate energies for k points in the Brillouin zone not related by the symmetry operation, by the symmetry operations R. I will stop at this point in this particular segment of my talk, and I will continue later with what is the shape of the this thing Brillouin zone in which we will usually work, and I will also discuss a little more about the star of k vectors and the small representations and so forth, but that we will talk in the next lecture, and I will stop at this point for this talk. Thank you.